This is Lecture 9C for a second example of a separable equation. Here's example 2 for separable equations. This is from Stewart problem number 37 for the rate of change of the concentration of some substance in the blood. In this equation, C is the concentration of the substance in the blood. R is the rate at which it is being injected, say through some IV drip. And K is a constant for the body, or typically the liver, the liver and the lungs, elimination of that substance. We call that K. And here's the differential equation governing the situation. The rate of change of the concentration with time equals the rate at which it's being injected minus Kc, which is the elimination from the body. So what do we have here? We have everything we need. It's a first-order differential equation. It can be separated. When it's separated, all the C terms, remember C is not a constant of integration here, it is the concentration in the blood, which is one of the reasons I chose this. We get so used to calling all constants C that when we see that same letter in a different context, it takes us a while to make the connection. So here we're trying to make that connection that C here is not a constant, but instead is the name of the function we're looking for. It is the concentration of this substance, of this drug in the bloodstream. Okay, so I'm going to separate this because I'm going to pull all these terms over to the other side. So I get 1 over R minus Kc dc by dt equals 1. That's okay. I've left 1 on the other side. It is not a function of concentration. Now I'm going to rearrange and then integrate. So here's how I rearrange. I have 1 over R minus Kc times dc equals 1 times dt. Now I'm going to integrate both sides. These are indefinite integrals. I'm going to integrate this side. I get something on the next page. Here I'm showing both pages together. So we have rearranged, and now we're going to take the indefinite integral of the left-hand side, the indefinite integral of the right-hand side. If I take the integral of 1 over R minus Kc, get minus 1 over K times the natural log of R minus Kc plus some constant of integration, which I'm going to call A1. On the other side, I get T plus a constant of integration A2. I'm doing all the steps here since it's this is only the second time you've seen this solution. So the next step, both constants can be and should be combined into one constant of integration and placed on the right-hand side. So we now get minus 1 over K times the natural log of the rate minus the elimination constant times the concentration equals T plus A being our constant of integration. That is the end of the calculus for this problem. But now to find the dependent variable, which is C, we have to use algebra. As before, we use exponentiation to recover C from the argument of the natural log function. So I'm going to erase both sides as powers of E, because the inverse relationship between E and natural log, the left-hand side becomes R minus Kc. The right-hand side becomes E to the minus Kt times E to the minus Ka. All right, this is a constant. Actually, let's rearrange and eliminate and isolate C at this time. So the concentration in the blood equals the rate of injection minus the rate of elimination minus 1 over K e to the minus Ka e to the minus Kt. This whole term here is one big constant. Because A and K are constants, we'll replace all of that with just the letter A. So here again we have the general solution, which is the concentration is equal to R over K, the rate at which it's injected, minus K, which is the elimination constant, plus some constant A times E to the minus Kt. I would like to evaluate this constant A. That's what I'm going to try to do. And to do that, I'll use the initial condition that when time is 0, C is C naught. evaluating at t equals 0, that's what I'm doing here. So we want c of 0 equals c naught, so I have to put 0 for every t in the equation, particularly that one. I have r over k plus a e to the minus 0. E to the minus 0 is 1, so this becomes r over k plus a. I can solve for a, and now I find a value for the constant of integration. It is C0, the initial temperature, minus the equilibrium value of r over k. So here is the particular solution for the concentration of the drug in the body for this particular kinematics. The concentration at time t equals an equilibrium value r over k plus the initial condition minus r over k e to the minus kt. Now the solution contains two terms. This is seen frequently in solutions of time-dependent differential equations. One is the steady state term. Okay, here's the steady state term right here. It does not depend on time. The other is the transient term. Here's the transient term here. What it consists of in this case is the initial condition minus the equilibrium condition times a decaying exponential. So this transient term decays away, and what you have left is the steady state term r over k. Graphically, when you graph this out, this is the steady state value is the equilibrium value, and since these solutions will approach the equilibrium line, which they will because that the last term in red there is a decaying exponential. It decays away, leaving only the equilibrium solution as a limit. So these the solutions, the nearby solutions, approach the equilibrium value, so this is a stable equilibrium. Here is a rather hard to read graph of the situation. So in this particular case, the dashed line here is the equilibrium value, and that's r over k. Here's the differential equation that we were solving. I'll write it bigger so you can read it. Okay. We use the method of separable equations to solve it. All right. And when we did that, we found a solution that looked like this. Equals r over k, the equilibrium value, plus, and now it's the initial value. Here the initial value is 0. Here the initial value is, well, I guess it's about 800, minus the equilibrium value of r over k, e to the minus kt. Okay, so if you start off with the concentration C0 less than the equilibrium value, okay, C0 minus RK is, C0 is less than RK, so this is going to be negative. All right, you can work through this. You can also look at the derivatives, and you find that that solution will increase. It'll be concave down, and it will approach the equilibrium value. If you start with a concentration greater than what is being infused, then as time goes on, your concentration will decrease and approach the equilibrium value of r over k.